MedCram.com.
Reducing your blood sugar, and it has nothing to do with what you're eating or exercise. This is Dr. Roger Schweld here for another MedCram video. If you are longtime listeners, you will know that we have talked extensively about the ability of light to impact our metabolic health. We talked about this study before called Associations of Outdoor Temperature, Bright Sunlight, and Cardiometabolic Traits in 2 European population-based cohorts. 13,000 people signed up for this study in both the Netherlands and in England, and they found that if you had more sun in the previous 7 days before a blood test, you had a better chance of having more insulin sensitivity and less diabetic profiles. And we talked about this in our Light as Medicine video, which I highly recommend. We've gotten more comments and more emails saying that this video changed their life. Because in that video, we talk about not only sleep, but we also talk about daytime and being awake and getting outside and what effect that has on things like the mitochondria and the matrix and reactive oxygen species, electron transport chain. If you want a deep dive into the metabolic health of your cell and why light is important, I highly recommend, among other things, watching Light as Medicine on our channel. Put that together with our video on long COVID from bad fat metabolism, which showed that when you go from a healthy state here to a post-COVID and even a long COVID state, notice here that there's generally a blue hue to these enzymes that are involved with fatty acid metabolism in the mitochondria, to a red hue here. There's a huge distinction, especially in our post-acute SARS-CoV-2 patients, that there is a definite slowing down of fatty acid metabolism. That's exactly what we think is going on. Today, what I want to talk about, though, is not infrared light, which we've been talking about before, but actually just red light. Near infrared radiation you cannot see. It's felt as heat, warmth from the sun. But red light therapy you actually can see, and there's a lot of lighting and products that you can buy that have red light. And I want to show you here how this red light therapy in a very well-designed randomized controlled trial showed that this can reduce glucose levels, especially when being challenged with an oral glucose tolerance test. I want to remind you that we maintain MedCram.com, which is a continuing medical education website designed not only for healthcare providers, but also lay people. We do offer CME units, and we cover everything from congestive heart failure to COPD to kidney failure. We also talk about ABGs, EKGs, chest x-rays, and how to interpret those. Let's get to the study. This has been published on Research Square, titled Optical Stimulation of Mitochondria Reduces Blood Glucose Levels. It's out of the University of London, authored by Michael Powner and Glenn Jeffrey. And it has just been posted in the last month, and it has not yet been peer-reviewed. But before we get into the details of this, we've got to review a little bit of the nomenclature and the definitions and things of that nature of cellular respiration and what actually goes on in the mitochondria. So bear with me as we talk about that briefly. It'll make what we're about to cover a little bit more understandable. So here you have the bane of existence of the biochemistry student. It's basically the mitochondrion, which is the basic organelle of energy production in the cell. And what is represented here is you've got glucose, which is right here, undergoes glycolysis, or if you like, glycolysis, which breaks down that glucose into 2 3-carbon units called pyruvic acid. In that process, you actually get some energy, net energy out by direct synthesis, substrate level phosphorylation, and you get 2 ATPs. ATP is the basic unit of energy in the cell. But this pyruvic acid then goes into the mitochondria, which are these organelles in the middle of or in the cytosol of the cell. And acetic acid gets converted into and then enters as acetyl-CoA into something called the citric acid cycle, otherwise known as the Krebs cycle, otherwise known as the TCA cycle. There's different names for it, but basically what's happening here is you have the cycle going around, and as a result, you get another 2 ATPs, but more importantly, you get these very reduced electrons. These electrons are high-powered, and they are all shuttled in the form of NADH and FADH2 to something called the electron transport chain. Now here in the electron transport chain, as those electrons start to go down a cascade from high energy to low energy and being passed on finally to the lowest energy acceptor, which is oxygen, to make water, protons are being pumped into this dark area called the inner membrane space, and that causes the pH in that space to drop because there's a high concentration of protons. These protons are then funneled through very specific filters. This is kind of like the exit holes on a dam. And as they go by, they are turning the turbine. But in this case, instead of turning the turbine and creating electricity, it's making ATP. And it makes quite a lot of ATP. As it turns out, 32 ATPs per molecule. So you can see here clearly, if we're talking about energy, that glycolysis or glycolysis and this substrate level phosphorylation is not making much energy. The real energy that's being made is here in the mitochondria and specifically at the ATP synthase enzyme. So anything that is going to speed this process up is going to create more ATP and it's going to utilize more glucose. But notice that there is another end product to all of this cellular respiration, and that is carbon dioxide. What comes out of this process is carbon dioxide. As this process accelerates, you're going to have more ATP, more carbon dioxide, and less glucose as it's being used up. And this whole process, as it gets revved up, is going to increase your basal metabolic rate, which is important if you want to lose weight and you want to be healthy and you want to have enough energy to sustain your cellular resources. So let's take a look here and see what the researchers knew prior to this test to see why they did this test. And it's right here in their introduction. This is the background to what they knew was going on before they conducted the study. They say here red light, and let me stop right there. This red light, part of this is in the visible spectrum. Some people would say up to 760 nanometers. I guess it depends on the person, but generally speaking, most of this is visible red light, not infrared light, which is invisible. They say here it stimulates mitochondrial respiration and shifts the metabolism. This photobiomodulation alters cellular respiration rate, increases membrane potential, ATP production, and subsequently reduces reactive oxygen species and inflammatory markers. And they have references for that. And of course, we'll put the reference to this paper in the description below. This results in improved sensory and motor function, including aged human color perception, 670 nanometers, which is the wavelength that we're talking about in this study, and other longer wavelengths of red or near infrared are absorbed by the nanoscopic interfacial water layer surrounding mitochondrial ATP rotor pumps. The energy transfer reduces water viscosity, allowing the rotor pump to achieve greater momentum and increase ATP production. Let's take a look at that again. Let's go back. They're saying that there's a rotor on this enzyme, and near infrared and infrared radiation allows this water around here to become less viscous. So this is able to spin faster and you're able to make more ATP. They go on. An increase in ATP production rate requires more fuel. What we're seeing here is that as this starts to speed up, it's going to speed up this whole process, and that is going to reduce your glucose concentrations. They go on and say glucose is the primary fuel source in animals, and as shown previously, systemic glucose concentrations decrease in an invertebrate model bees. So these authors have also done previous research that showed exactly what we're going to show today in bees, and this is the first time now that they're showing it in humans and they're ready to publish. And the reason why they believe this is going to happen in humans is because they believe a lot of the enzymes that fuel the mitochondria in bees are preserved and conserved in the enzymes that are in man's mitochondria. Finally, what they say here is, here we have extended these findings from invertebrates into humans, demonstrating that non-pharmaceutical, non-invasive optical interventions can be used to support blood glucose level management. Let's take a look and see if they were able to do that. They did a study, and here they involved 30 subjects, which is not a lot, but if you're able to get statistical significance with 30 subjects, then that shows that it's a pretty powerful effect. And they randomized them. That's important to know because randomized controlled trials don't involve bias, they don't have confounders, and it's one of the highest levels of evidence when you're looking at a study. The first group is what we'll call the placebo group. And the second group is the 670 group, and that's simply referring to the nanometers that they're actually going to get, 670 nanometers. So what happens to this group? Both of them have a glucose tolerance test. That glucose tolerance test is basically 75 grams of glucose in 150 milliliters of water, and their blood glucose and carbon dioxide levels are measured. So they're measuring exhaled carbon dioxide, and they're also getting plasma glucose concentration checks. Nothing is being done to them in both of these situations. We're going to call this the no placebo in the placebo group because they know here that they're not getting any treatment. They don't know which group they're in, of course. It's blinded. But they're not getting any sort of treatment. They're just coming in and getting a baseline test where they ingest a bunch of sugar and they see what happens to their blood glucose and what happens to their exhaled carbon dioxide. Same thing over here in the 670 group, except here we're calling it the no 670 test in the 670 group because they're not getting anything done to them here. So this is the control group for both. Less than 7 days later, so it had to be less than 7 days later because we didn't want anything to change much with their metabolism. They then, in the placebo group, get a placebo and another glucose tolerance test. And here they get 670 nanometers of light and get the glucose tolerance test. Let's talk a little bit about how they got this light. They got this light for only 15 minutes, and the power of that light was 40 milliwatts per square centimeter. They got this light on their back over an 800 square centimeter area, which is about a square foot. And the light was 40 centimeters away from the subject. It was given 45 minutes before the glucose tolerance test. Let's review. It was given 45 minutes before the glucose tolerance test, only for 15 minutes. It was held 40 centimeters away from the patient. And on the patient, it radiated 800 square centimeters at a power of 40 milliwatts per square centimeter. Most of the red light fixtures or products that you can buy on the internet range above this. They're usually around 60. Some of them go to as high as 100 or even more. So this is not a very powerful light. When they put this light on the back of the patient, it was sealed off to their skin so that they could not tell whether or not the switch was on or off. And that's how they were able to get the placebo. So they would put the fixture on the back of the patient, and so they could not tell. The only difference between the placebo and the actual intervention group was someone turned the switch on versus someone turned the switch off. And of course, it was on their back, so they couldn't see it. Let's see what the results were in terms of glucose. And I've color-coded these groups. It'll make it a little bit easier. We're going to look at blood glucose after the glucose tolerance test, and we're going to compare the placebo to the actual intervention here on the next graph. Let's take a look at that. So green is the placebo, red is the intervention. Blood glucose, and this is measured in millimoles per liter. If you want to convert this into milligrams per deciliter, remember that 1 millimole per liter is equal to 18 milligrams per deciliter. This is what it was at the resting baseline, and this is how much it went up. And you can see here clearly at around the 45-minute mark and the 60-minute mark, there was statistical significance, actually in many of these places, that those that were on the placebo had higher glucose concentrations than those that were irradiated 45 minutes before this glucose tolerance test. For only 15 minutes at 600 nanometers, there was a statistically significant less blood glucose concentration. Now what we're going to do is compare these two groups here, the intervention group, with, in the same group, those that just had a regular glucose tolerance test without the light strapped to their back. The people in the intervention group that did not have this 670 nanometer light, very statistically significantly different compared to the same group of people when they did get it, very different glucose concentrations. So the next graph I want to look at is these two groups here to see if there's any difference between those. We see here that there is no statistical significant difference between any of these groups here. You can see that very clearly. Let's go ahead and now talk about the maximum glucose concentrations that we saw in those groups. Remember that this is the placebo group as the baseline. This is the placebo. This is the baseline in the 670 group, and of course the intervention. And what we can see here is no statistical significant difference between the placebo group, no placebo and placebo, but there is a statistically significant difference between in the 670 group when they got the 670 nanometers of light and when they did not get the 670 of light. And of course, there's statistical significance here as well, which is the point of the study. Let's review here again. When we irradiate with red light that's visible, what the study authors indicate is that there is an effect on the water around this pump that allows it to spin faster, and it reduces the concentration of glucose and also at the same time increases the basal metabolic rate. And there seems to be very good evidence to that. Could it be that the glucose is just going down because of some other mechanism? If this is truly happening, we should also see carbon dioxide levels go up. So that's what we attempted to look at here. Let's see if that happens. And so the first thing we're going to do here is look at carbon dioxide levels between these two groups. There is an increase in some places and a decrease in others between the placebo and the 670 nanometer group. And at no point here along the way was there any value that was statistically significantly different than the other. But, as I say often, the absence of evidence does not equal evidence of absence. So it could very well be in this study that it was underpowered and they couldn't get a statistical significance. Let's take a look at the difference between these two groups, because it could very well be that randomization may not have been good, but if we go and see a difference between these two groups, that might mean something. And that's, in fact, what we see here. That end-tidal CO2 did go up with the glucose tolerance test, but it went up statistically significantly more when they got the 670. And so what does that mean? It means that the reduction in glucose must be due to, at least in part, an increase in the metabolic rate at that time, with more consumption of glucose turning into ATP. Let's again look at these two groups and see if there's any difference. We should not see a difference between those two groups. And in fact, we don't. So it seems as though there is good evidence that frequencies of light that come from the sun that are powerful enough to go in and through the skin and down into the tissue and to affect the mitochondria can in fact improve mitochondrial function and also metabolic health. We saw this already on a population level. We saw this in populations where in the previous 7 days, if we looked at the weather reports and we saw that there was more sunlight in those 7 days, that on average, those subjects getting the blood test had better metabolic health than those with less. And this shouldn't be a surprise. We've also talked about this with this study. This was a study that looked at near-infrared radiation in COVID-19 patients. And I highly recommend that you go back and look at this because this is an amazing study looking at another randomized controlled trial showing that near-infrared radiation from LEDs, when placed on patients who had mild to moderate COVID-19, improved and got better than those that did not. And they got better in terms of their white blood cells, pulmonary function tests, in terms of their oxygenation, and a number of variables. This has been a journey for me. If you look back at the COVID-19 videos that we did at the very beginning of the pandemic, and even after that shortly, I've started to research this, looking at oxidative stress, and it's become very clear to me because of what has happened in the different countries around the world, what has happened to developed countries versus non-developed countries, why we had, for instance, 4% of the population of the world, but 25% of the COVID-19 cases, why we have an epidemic of depression, obesity. It's because, in part, we're not getting outside enough. We are stuck on devices, computers, and we're not getting outside. And this is not a hypothesis. We know that 93% of our lives are inside. We get up in the morning, go to our car in our garage. We drive in air-conditioned cars to work and work all day in offices that have low-E glass that don't let near-infrared light in, under fluorescent bulbs or LED bulbs, and then we drive home and the sun is down, turn on the television and watch that past 9 o'clock. We wonder why we're plagued with such rates of obesity and things of that nature. Whereas in countries that are not as developed or technologically advanced, where they're not on computers all day and they're going outside and they are doing practical things with themselves, getting sunlight, working, exercising, breathing fresh air, these are the countries that actually had less COVID-19 mortality, have less obesity rates. And what we were surmising at the population level with ecological studies, we're now starting to confirm on the microbiological level and the biochemical level with studies in the laboratory. And I don't want you to mistake the point in this. The point here is not to go out and buy a red lamp, although you can certainly do that, especially if you're living at northern latitudes and the sun is not out some times of the year. The point here is that we need to get outside and take the benefit of the largest free near-infrared and red lamp in the solar system. Thanks for joining us.